Having completed the recent section, let's next see some exercises. Let's start with this second one. X is a topological space, that's understood, and there are actually two topologies on X, one at a time of course, tau and tau prime. These are topologies on X such that tau prime is strictly finer than tau. Then what can you say about the subspace topologies tau y and tau prime y for some subset y of X? Will they also be comparable? If so, exactly how? And the answer is yes, they are comparable, and this is the precise relation. Tau prime y is finer than tau y. Actually, there is no need to write anything else here, I mean, as far as the first part is concerned, but still I will elaborate exactly why this is true. This is the reason. For any open set u coming from tau, we have u also in tau prime, because tau prime is finer than tau, that's why. And that is why u intersection y will belong to the subspace topology tau prime y by the definition of subspace topology. However, this is how elements in tau y look like. They are intersections of open sets in tau with y. So that means every element of tau y is inside tau prime y. So that's how you get this comparison, that tau prime y is finer than tau y. However, it's not necessary that you have strict containment here. And we write that here, however, we don't necessarily have this strict containment. That means tau prime y is not necessarily strictly finer than tau y, although it's always finer than tau y. To see why, you consider this example. Let X be this three element set consisting of A, B and C. Let Y be the singleton set consisting of A. Let tau be this topology on X consisting of these open sets. The empty set and X of course will be there, but besides them we have this singleton set A, singleton set B and the pair set consisting of A and B. You can verify that this is actually a topology on X, and the larger, or I mean the finer topology tau prime is P of X. P of X means the power set of X. This is of course the topology, it is actually the discrete topology on X. So are we having the hypothesis of this situation? I mean, yes, tau prime is of course finer than tau, actually strictly finer than tau. For example, in this topology, the singleton set consisting of the point C is there. That's an open set in this topology, but that's not open in this topology because it's not present there. So this is strictly finer than tau. However, for this y, if you calculate the corresponding subspace topologies, you will see that they are equal. So still that relation, I mean this thing is there, but it's not strict anymore. I want you to do that part yourself. Let's next see number 4. A map F from X into Y. In this context, X and Y are both topological spaces, is said to be an open map if for any open set U in the domain space X, F of U, its image under F, which of course is a subset of Y, is also open in Y. If this happens for all open sets U in X, then we say that F is an open map. Now this is what we have to prove. We have to prove that for two topological spaces X and Y, if we consider their Cartesian product, in the product topology of course, then the projection maps pi1 and pi2, which you already know by now, are open maps. And this is the solution. For any open set U in X, that means U is a subset of X which is open in the topology that X has, whatever it is. And any open set V in Y, the pi1 image of U times V, the Cartesian product of U and V is equal to U, and of course that is open in X because that's how we chose it. And the pi2 image of U times V, which is V, is open in Y. You think yourself why this image is U and why this image is V. You just go back to the definitions of pi 1 and pi 2 and it will become clear very quickly. And then we just suddenly write, because of this, pi 1 and pi 2 are open maps. How? Well, actually it's quite easy, but still I have not written all the details. What does the definition say? The definition requires the F images of all open sets in the domain space to be open in the codomain. I mean, if we call that codomain. For pi 1, the domain space is X times Y in the product topology. Are we considering all open sets in the product topology here? Not exactly. We are only considering basis elements. So we have shown that, okay, the pi 1 images of the basis elements of the product topology, which are also open by the way, are open in the codomain space, which in this case is X. But how does that automatically imply that pi 1 is open? Will the pi 1 images of all open sets be open? Yes, because any open set is an arbitrary union. Arbitrary union means any type of union of sets of this type, and direct images of unions equal unions of direct images. You can use that property from function theory. So that means because these pi 1 images of basis elements are open, so their union will also be open in X. So that's how you can link the two things, and you have the fact that the pi 1 images of all open sets are actually open. That is why pi 1 is an open map. Similarly, pi 2 is also an open map. Before I leave this solution, I want to say something about the way I write things. I suppress many details, okay. So if you look at my solutions from the point of view of a formal solution, they will look very incomplete. I am not saying that these are ideal solutions. They are not in most cases, because I don't write everything. And that is because if I start writing absolutely everything, the videos will become very long. So you should supply details. For example, here you should really write what happens after this, then only you write this final sentence. Okay, so you do those things. Don't just simply copy these things and use them as they are. These are less solutions and more hints. Let's see another one, number 6, where we have to show that the following countable collection is a basis for the plane R2, where the collection consists of sets like this: Cartesian products of open intervals a comma b times c comma d, where a is less than b and c is less than d, and a, b, c and d are rational numbers. Q is the set of rational numbers. So if you think of it geometrically, it is just like one of the bases you have already seen for this topological space R2, which geometrically it's the two-dimensional plane. Do you recognize what type of sets you are looking at? These are interiors of rectangles, that basis, where the rectangles have sides parallel to the axis. But it's not exactly that basis. In that basis, all possible rectangles were considered. Here, however, the corners of the rectangle, or to make it less mysterious, these real numbers a, b, c and d are rational. There they could be any real numbers, that original basis. And the solution is very compact, a short solution. By exercise 8a of section 13, so it's that section which has the name basis for topology, that thing. At the end of that section, you have exercise 8, where part A has this fact, that this collection is a basis for the topological space R, that means our line. Just like this one, here also we are considering a comma b, open intervals, ordinary open intervals where a is less than b, but a and b are rational numbers. Because of this fact and theorem 15.1, we directly get this result. You go and see the statement of theorem 15.1, you will instantly realize why. I won't say anything more on this. However, I will draw your attention to this word, countable. That means this topological space has a basis that is a countable set. Countably many open sets can generate the entire topology. You will see later why this is important. I mean, topological spaces which have countable bases are special. Some topological spaces are so large that they do not have countable bases.